Good morning, I'm Cristal Navarrete from 4CHB and I'm here to discuss a problem regarding mechanical energy balance. An electric motor supplies 70.42 kilowatts to a pump with an efficiency of 0.8 to deliver 50 liters per second of water from a large tank 1 to a large tank 2 elevated at 100 meters. Note that both tanks are open to atmosphere. Determine the exact diameter needed if the steel pipe is 200 meters long and contains a T and two 45-degree elbows. A diagram is important especially in these kinds of problem in order for us to identify the reference points wherein the given will be based. So here, we put reference point 1 in the level of the water in the first tank and the reference point 2 in the level of the water in the second tank. We base the elevation given in the problem to the reference points we made. So, first, we should write the mechanical energy balance. So, the friction loss plus the V delta P plus the change in kinetic energy plus the change in potential energy equals the shaft work if there is any. Based on the problem, we can say that V delta P is going to be 0 because we said that both tanks are open to the atmosphere. So we assume that both tanks have the same pressure, which is the atmospheric pressure. Also, we can cancel the change in kinetic energy since our reference points are only the two levels of water, and we can assume that this water has no movement or it has the 0 meter per second velocity. So now we're left with the friction losses and the change in potential energy equals the shaft work in the problem. So we should identify the values individually. So first, let's get the value for the change in potential energy. The change in potential energy has the formula of delta Z G over GC. Delta Z pertains to the change in height. So in the problem, we have 100 meters. We just substitute the values. 100 times 9.81 over 1 equals 981 joules per kilogram. Note that I used SI units in solving the problem since we are given SI units in the problem. So now I got the value for the change in potential energy as 981 joules per kilogram. Next, we should get the shaft work made to the pump. So what the given is only the actual power. So we need ideal power in the mechanical energy equation balance. So remembering the equation or the formula for the efficiency of pump, which is W ideal over W actual, we can now solve for the W ideal since we are given the efficiency of the pump and the W actual. So W ideal will be the efficiency of the pump, which is 0.8, times the actual work, which is the given value, the 70.42 kilowatts. But then we have to convert this value into an energy unit, which is the joules per kilogram. So first, we use the conversion factor 1000 watts equals 1 kilowatt to convert this into watts. Then we divide the whole value into the mass rate. So how do we get the mass rate? We get the mass rate from the equation M equals volumetric rate times the density. Since we are given both of these, we can now get the mass rate. So substituting the values, 50 liters per second times 1000 kilogram per meter cube. But take note that we use conversion factors in order to get a value or the unit that we need, which is kilogram per second. So the value that we got is 50 kilogram per second. Now we can substitute this value to this equation to get the value for the W ideal. So the W ideal will be 0.72 joules per kilogram. We have the value for the change in potential energy and the shaft work. Now we are going to get the value for the summation of the friction losses. The friction losses in this problem will be the summation of the line friction. And we can see that from this point, from the tank to the pipe, there is contraction. So we assume that there is friction due to contraction, which we will say as Fc. And we also put a reference point 3 so that we can name the properties of water here. Later you'll see. So here you can also see that there is a sudden expansion. So there is a friction due to expansion that we will name as Fe. We should get these values individually by the formulas given in the handbook or in the Jean Copley's book. So first we'll get the Fc. Fc has the formula of Kc times velocity squared over 2gc alpha. Alpha is a correction factor for flow, but since we are given water, we assume it to be turbulent. And for turbulent flows, alpha is 1. So this is going to be 1. Now, you are going to ask, what will be the velocity that we are going to use? Now, this is what I'm saying a while ago, why we put the reference points 3 and 4. So, from this equation, we can say that the velocity here is the velocity of the water in the pipe, which is from the contraction. For the contraction is the point 3. So we name this velocity as velocity 3, so v3. And then we get the values for this so that we can get the value for Fc. So Kc has the formula of 0.55 times 1 minus d3 over d1 squared. Take note that the diameter in the numerator is always the smaller diameter. And we can say that here, 3 has a smaller diameter than this one. And from the figure, we can say that the diameter of the large tank 1 is much larger than the diameter in our reference point 3. So we assume this to be negligible. And we are left with the value of 0.55 for Kc. Velocity changes when diameter changes. And since diameter is what is asked, we should represent V in terms of D. We can represent V in terms of D by using the formula V equals the volumetric flow rate over the area. And the volumetric rate is given, and the area we can represent as pi over 4 d squared. From the volumetric rate, from this mass rate, we can say that it is 0.05 meter cube per second using these conversion factors until here. So this is 0.05 meter cube per second. And getting the value for this, we get 0.02. We get 0.2 over pi d squared. We can substitute this value to this value so that we can simplify the value for Fc. So, substituting everything, we got 0.55 times 0.2 over pi d squared over 2 times 1. We say that this is going to be 1.11453302 times 10 to the negative 3 joules per kilogram. Next, we need to find the value for Fe. Fe has the formula Ke times V4 squared over 2gc alpha. So, from the figure, we can say that the velocity in a reference point 3 is equivalent to the velocity in a reference point 4 since they flow in the same pipe with the same diameter. So this V3 is equivalent to V4. So we just substitute this value to this to simplify the value for Fe. But then first, we need to get the value of Ke. Ke has the formula of 1 minus d4 over d2 squared. Like in this situation, we can say that the diameter of the large tank 2 is much larger than the diameter of the pipe in the reference point 4. So we assume this to be neglected, and Ke will have the value of 1. Substituting everything again, 1 times 0.2 over pi d squared over 2 times 1, we get 2.02 64 times 10 to the negative 3. But this is a common mistake to many. We need to remember that there is a d to the fourth remaining in the value of Fe. So there will be d over 4. So like I said, there is a common mistake. I forgot it here. So the Fc value is this. Don't forget the over d to the fourth. And the value of Fe is this. Lastly, we need the value for the line friction in order to get the overall or the summation of the friction losses. So the equation for the line friction is 2F velocity squared change in L over Gc times D. D is unknown, so it will remain. We need to get the value of F and the change in L. We have the value of velocity from, this is the value of the velocity that we are going to substitute here later. So F has the value, let's first get change in L. So change in L is the sum of all the lengths of the pipe, including the fittings and the valves. So we have a given length for the pipe, which is 200 meters. And let's add the length of the fittings and the valves. So in the problem, we have a T and the two 45-degree elbows. From the Jean-Copley's book, we are given the L over D values for these kinds of fittings and valves. For a T, we have 50 as the value of L over D, and for the 45-degree elbows, we have 17. Multiplying by the number of the T and the two elbows, we obtain plus. Since this is L over D value, we need to multiply this to D. Don't forget that. So we have the value of 200 plus 84D. Now we have the value for the change in L. We're left with the value of the friction factor F. So the friction factor F has the formula negative 4 log times 0.27 times the roughness parameter over the diameter plus 7 over the Reynolds number raised to 0.9, and then this whole equation raised to a negative 2. The roughness parameter for steel is 0.0457 millimeter. So we need to multiply this to 10 to the negative 3 in order to get the value in meters. But then we need to get the value for the Reynolds number. The Reynolds number has the formula of dV rho over mu. D is missing, so let's leave it there as a variable. V, we have the value of velocity. Then the density is given 1,000 and the viscosity is 0.001. So substituting everything, we obtain the Reynolds number of 63,661.97724 over D. See that this D and the square here will cancel, and then we'll be left by this value. So now we can substitute this to this and everything else to the back to this, and we'll get the value of D. As you can see, I summarized everything that we have obtained a while ago in this piece of Manila paper. We got the change in potential energy, the shaft work, the friction due to contraction, and the friction due to expansion. This is the simplified value for the FL. It is not necessarily simplified, but I substituted everything like the F, here, the whole F, and the velocity. As a technique, we assign these values as letters in our calculator. Like in Casio, we can assign values for letter A, for B, C, D, and so on. So, here we can assign the change in potential energy as A, the the shaft work obtained as B. So in FC, we can say that we can put this constant as C. For FE, this constant as D. And the other constants that will consume the space in our calculator as letters. So we have A, B, C, D. This is too long to be put in our calculator. So this 1.2339 times 10 to the negative 5 will be assigned as E. And the Reynolds number, the constant in the Reynolds number will be represented by F. So, substituting everything, we can now obtain the value of D. So, to save space, we need to put pi d squared from here to here. So, let's erase this and put it here. So, the final value of our denominator will be pi d cubed. Sometimes it would take a few seconds or even a minute before the final answer come out of your calculator. So, now it took some seconds for the answer to be released in the calculator. The final answer is 0.15968 meter, or to give this a more appealing appearance, we can say that the answer is 159.68 millimeters. So, the size of the diameter needed to deliver the 50 liters per second of water from tank 1 to tank 2 is 159.68 millimeter. So the diameter here in the pipe that will deliver is, thank you.